When you first look at a bunch of data, it can feel like pure chaos, right? A total jumble of numbers and measurements. But what if I told you that underneath all that randomness, there's a hidden order? There are patterns, there are truths. Today, we're going to learn the language that lets us see that order. We're going to build the entire framework of statistical thinking, right from the ground up. So our objective is simple: to master the language of chance. And this isn't just about crunching numbers. It's about learning a systematic way to think about uncertainty so we can quantify the truth that's hiding inside our data. This entire journey is powered by two deeply connected fields: probability and statistics. And here's our roadmap for the journey. We're going to start with the absolute basics of probability. Then, we'll use that foundation to understand something called random variables and their common patterns or distributions. And finally, we'll see how these incredibly powerful ideas called limit theorems build a bridge from theory to the real world, which lets us perform what's called statistical inference. Okay, let's get into it. All right, first things first, we need a language, a way to talk about uncertainty with precision. Probability gives us the grammar and the vocabulary we need to make sense of random phenomena. Everything really starts with three core ideas. First, we have a random experiment. That's just any process where we don't know the outcome ahead of time, like flipping a coin. Second, we have the sample space, and we use the Greek letter omega for that. It's simply a list of every possible thing that can happen. For a coin flip, that's easy, just heads or tails. And finally, an event is the specific outcome we actually care about, like, say, the coin landing on heads. The best way to think about it is like this. That entire box is the sample space. It's the whole universe of possibilities. The circle inside is our event, the specific thing we're looking for. So how do we calculate its probability? Well, in the most straightforward cases, it's just a simple ratio: the number of ways our event can happen divided by the total number of possible outcomes out there. Now, for this whole system to be logical, it has to follow three simple, unbreakable rules. We call them axioms. First, the probability of any event has to be a number somewhere between 0 and 1. 0 means it's impossible, 1 means it's absolutely certain. You can't be less than impossible or more than certain. Second, the probability of the entire sample space is 1. This just means something from our list of possibilities has to happen. And third, the probability of an impossible event is 0. That's it. These three rules are the bedrock for everything that follows. Okay, so what if we want to figure out the probability of one event or another? We use something called the addition rule. Now, for the general case you see on the left, we can add the probabilities of A and B, but then we have to subtract that little overlapping part, their intersection, because otherwise we'd be counting it twice. But if the events are mutually exclusive, like on the right, they have no overlap at all. So in that case, you can just simply add their probabilities together. This brings us to one of the most important, most powerful ideas in all of statistics: Bayes' theorem. You can think of it as an engine for updating our beliefs when we get new information. Look at the flow. We start with a prior belief. That's what we think is true before we see any new data. Then we get some new evidence. Bayes' theorem is the mathematical machinery that lets us combine that prior belief with the new evidence to produce an updated, smarter, posterior belief. It is the formal, logical way to learn from the world. So we've defined events, but data analysis needs numbers, right? The next logical step is to translate these abstract outcomes into real, concrete numerical values that we can actually work with. And that is the job of the random variable. Random variables pretty much come in two main flavors. On the left, we've got discrete variables. These can only take on specific, countable values, like the roll of a die. You can get a 1, a 2, a 3, but you can't get a 2.5. We visualize their probabilities with a bar chart, which is technically called a probability mass function. Then on the right, you've got continuous variables. These can take on any value within a range, like a person's exact height or the amount of time you wait for a bus. We represent their likelihoods with a smooth curve, called a probability density function. And for these, the probability isn't the height of the curve, it's the area underneath it. Once we have a distribution, we need a way to summarize it. The two most important measures are the expectation. You probably know it as the mean or the average, which is basically the center of gravity for the distribution. And then there's the variance, which tells us how spread out or dispersed the data is. A low variance means the data is all clustered tightly around the mean, while a high variance means it's really spread out. So it turns out that a whole lot of random processes out there in the world actually follow very predictable patterns. These patterns are what we call distributions, and they give us incredibly powerful models for understanding our data. Let's start with a really important pattern for discrete data, the binomial distribution. This is your go-to model anytime you're counting the number of successes in a fixed number of trials. For example, if you flip a coin 10 times, what are the chances you get exactly 7 heads? Or if you test 100 products coming off an assembly line, how many are likely to be defective? Both of those questions are answered by the binomial distribution. And now, for the most famous, most important distribution of them all, the normal distribution, which everyone knows as the bell curve, is so common in nature and in statistics that some have called it the imprint of natural order. The beautiful thing about the normal distribution is that its entire shape is defined by just 2 numbers, 2 parameters. The mean, or mu, sets the location, the center of the bell, and the standard deviation, sigma, controls the scale, how wide or how narrow that curve is. Now, the normal distribution comes with this incredibly useful feature, often called the 68-95-99.7 rule. It is a fantastic shortcut. It guarantees that for any normally distributed data, about 68% of it is going to fall within 1 step, 1 standard deviation of the average. About 95% will fall within 2 steps, and almost all of it, 99.7%, will fall within 3. This gives us a really powerful way to quickly understand what's common and what's rare. So far, we've been living in the nice, clean, theoretical world of probability. But how do we connect all this theory to the messy data of the real world? Well, the answer lies in 2 of the most beautiful and important theorems in all of mathematics. And this brings us right to the central question of all of statistics. We almost never have data on an entire population. We usually just have a small sample. So how can that small sample possibly tell us anything reliable or meaningful about the entire group? The first part of the answer is a powerful guarantee called the law of large numbers, and it's actually a very intuitive idea. It just states that as your sample size gets bigger and bigger, the average of your sample will inevitably get closer and closer to the true unknown average of the entire population. It's simple, really. More data gets you closer to the truth. But the true magic, the real showstopper, is the Central Limit Theorem, or the CLT. Just watch how this works. Even if our original data comes from a distribution that is completely flat and uniform, as we start taking more and more samples and calculating their average, the distribution of those averages begins to form a bell curve. By the time we're averaging just 30 samples, it looks almost perfectly normal. It's incredible. So what's the big takeaway here? The Central Limit Theorem is the mathematical justification for why random sampling actually works. Because the averages of our samples will be normally distributed, we can use all the known properties of the normal distribution, like that 68-95-99.7 rule, to make precise probabilistic statements about a population mean, even if we know nothing about the population's original shape. It's the key. And that brings us full circle. We can finally put all of these pieces together to understand the fundamental process of how we learn from data, something we can call the inference loop. This diagram shows the entire process. Think of it like this. Probability starts in the theoretical world of perfect models, and it tells us what kind of data we should expect to see. Statistics does the exact opposite. It starts in the real world with messy, observed data, and it works backward to infer what theoretical model was the most likely one to have created it. It's this elegant, powerful loop between theory and observation. So we've built the whole foundation, from the basic axioms of probability all the way to the power of the Central Limit Theorem. This framework is the engine of discovery in science, in business, in everything. So I guess the only question left is, now that you have this tool set, what truths are waiting to be discovered in the data that's all around you?